such model classes realized. Then I will move to the phase effects in other magnets as an example of their conventional properties. And in the final part, I will discuss another type of unconventional magnets, namely odd parity or P-wave. So I will start from a very low level. So what are the magnets? Perhaps when we talk about magnets, we always mention a ferromagnet like this household magnets they found in my office, tracked metallic particles. So essentially everything that interacts with the magnetic field. And such magnets have a lot of applications, starting from some simple household items like this fridge magnet, compasses, electronics, dynamics, hard drives, transport, but it's not electronic transport, it's just transport. There are other classes of magnets, namely antiferromagnets, ferromagnets, diamagnets. How do we distinguish between them? So what makes them different? And to do this, we need to delve into structure of material. We need to understand how it is composed. So I will be talking about lattice structure. What is lattice? It's essentially the way how atoms are arranged in a solid. So here, for example, I'm showing a very simple crystal of natrium chloride, which is just salt that we use in kitchens. So here's the atom structure, which is part natrium and chlor atoms, and a very nice cubic crystal. So in magnetic materials, there is another property, which is the speed of such lattice atom. And simplest model of ferromagnet, which I think has to do with real materials, is just to arrange atoms in a square lattice and have them to have spin in the same direction. It is going to be a ferromagnet. It has a non-zero net magnetization. Its cousin, antiferromagnet, was described later by Louis Thiel. And in this case, we need to add another subspecies. We need to have two types of atoms with spin, let's say, up and spin down. This spread and will have two linear cells. And they compensate each other. On average, there is no net magnetization here. And such material shows different properties compared to ferro. Now, next step. Look at lights, but we also have electrons. We have charge carriers in this material. Let's add them to our, let's say, ferromagnet. To describe these electrons, we can write simple Hamiltonian. Use number one equation in any theoretical paper, where is a Hamiltonian? Here it is. It contains the kinetic part, T squared divided by 10, and of course, lattice potential, which essentially will define the properties of these electrons. And as we know from quantum mechanics, I think quantum mechanics 1, I'm not sure about curriculum here, that in the potential wave functions of electrons and the energy will be arranged in particular form and in particular levels. And in the case of crystal, the arrangement of atoms is periodic, potential is periodic, and hence wave function will require a very form for block function. Energies will be arranged on a set of energy levels, and it will form bands. Here I'm just showing the band structure for aluminum, and real crystal, our electrons exist in some particular volume in real space. Bands, on the other hand, exist in the volume in the momentum space. Momenta acquire specific values that confine to so-called realities. But for us, it's just important that there is a specific dependence between energy and momentum structures, which can be complicated, can be seen. So, in short, specific lattice potential leads to a specific arrangement of electron bands. But there's another ingredient that exists for this spinful materials, especially speed. Electrons also interact with the spin of lattice ions with the spin of chimeral particles here in the picture. And this leads to a modification of energy spectrum, of course. If we go to a ferromagnet and if we fix energy, for example, we can plot the following fixed energy spectrum. It's just a circle. I'm not showing any real material data, as we showed. So it's composed of single band where all electrons are still polarized in the same direction. If we go to antiferromagnet, we will have a doubly degenerate band, which is composed of spin up and spin down. As before, here we have some magnetization, here we have zero net magnetization. Now, what makes our materials unconventional? What are these unconventional magnets? So, an antiferromagnet, I'm just repeating the same figure. We have just spherical arrangement of our electron points. But what if we introduce an additional atom here on the side? It will deform electron pockets. It will deform our electron distribution around these atoms. And it will become slightly elongated here, there. Now, this was known, I think, a long time ago, and even Yale had described such types of antiferromagnets. What was different? What is different now? Difference is in the fact that before, in order to classify such antiferromagnets, we used magnetic spin groups. Now, in order to classify such new different types, we use the spin groups. What's the difference? In this case, spin groups are richer in the features. Magnetic groups, they combine spin flip and crystal rotation. In spin groups, these operations are independent, so we can have actually structure. For example, here, symmetry of such lattice is not inversion or translation. So here, for example, we can translate flip spin. Here, if we translate the flip spin, we don't match this ellipsis. We need to have a rotational symmetry. In this case, symmetry will be rotation by three. And such symmetry classification and usage of spin groups was essentially advanced by, I think, these people, Special, Nova, and Bugis. They use this group language to classify the materials. For such types of materials were appeared in paper before then, but they were not precisely classified. One is to remember. So, cannot say that these groups really discovered the material, but they made significant progress in actually systemizing our knowledge. So, what's the difference between this material with deformed orbits and antiferromagnet? The difference is that, unlike antiferromagnet, where we have doubly degenerate energy bands here, the bands are no longer degenerate in general, except for a few points here. On average, they still have zero net magnetization. But if we fix direction of momentum, we see now some magnetization. So this material called altermagnet, which comes from the word alternating, it combines some features of antiferromagnet and ferromagnet. So zero net magnetization, but some spin polarization along certain directions. And such a combination where we don't have net magnetization, but we have momentum dependent spin splitting, makes it unconventional. Unconventional means just not the same as antiferromagnet and ferromagnet were discussed before. And also, it's a nice word when you would like to publish in Nature and Science. So, before I delve into details and show Hamiltonians and cutting edge research, I would like to present my take-home message for those of you who are maybe not so interested in the details. So, what do we have in ferromagnets? We have strong spin response. We have net magnetization. Our response is usually somewhere in gigahertz range. And these materials are abundant, are known, well studied, widely used. What about antiferromagnets? Here, the spin response is weak. So, no net magnetization, hence, we don't really couple to magnetic fields, we don't really show any speed transfer. Our response is usually in terahertz range, which is good. We can have faster electronics out of them. And there was a surge of interest in antiferromagnetic spintronics some time ago, which used to lead to anything that we actually can use in our modern devices, but it was terrible. And these materials are also common and well studied. And therefore, conventional magnets. Now, unconventional magnets, altermagnets. These materials, as I mentioned before, combine two properties. So they have strong spin response. They have no net magnetization, Terabit range response, asymmetrical. They are limited. If I were a material scientist, I would say that there are thousands of materials discovered by database search, but I'm not. But still, there are many predictions. Experimentally discovered only, I think, a couple, 5 to 10. The people actually agree that they are magnets. More to come. Different materials have been discovered. And actually, some of them are drawn here at Science and Technology and studied at our place. And another part is all parity magnets that have a pretty complicated texture. So they usually require you to have some spirally or helical spin textures. They share almost the same responses as outer magnets, and sometimes people try to gather them in the common class like outer magnets, anti-outer magnets, but then it becomes too complicated. So I will call it just all parity magnets. Now, previous observation. So how do we know that these materials are ultimate? We can use technique called ARCS, angular resolved potential spectroscopy. This technique is essentially shining light. We get electrons out, we measure the momenta, energies, and then we can reconstruct band structure of material. So here is an example of data. Actually, it's a pretty nice example of ARCS data. One can indeed see that there are some bands here, and this is, I think, the derivative of the data. So, and we can, as we usually do for ARCS data, compare it with theory and see nice agreement here. So this agreement prompts us to conclude that finally stellarite is an ultramagnet. Furthermore, we can measure spin polarization of these bands, and it's indeed, if this is a spin down, I guess it's spin up. I will use different colors. Anyway. Another material that's actually weaker. It's intercalated TNT, cobalt, niobium 4, selenium 8. Its ARCS data is not so great here, right? Well, it's of course overlaid with theory data, but we don't really distinguish these two lines here. We can distinguish something in the intensity. So we can say that the intensity of spin up and spin down is different, which is a signature of all. But what they actually did, they used a slightly different technique, which is called angle resolved reflection ARCS, angle resolved reflection emission spectroscopy. And they can map out the cross section of current surface at fixed energy. This is momentum space, and this cross section shows a nice J-wave symmetry. So this material is J-wave ultramagnet. All right, what are the properties of ultramagnets? Ultramagnets show spontaneous flow, which is essentially interesting because we observe polar without magnetization. They show spin splitter effect, which is a generation of spin current perpendicular to the electric current. The magnets are chiral. They can show spin triplet superconductivity and locking chemical ferrite pairing with zero momentum. They show unusual thermoelectric effects in ultramagnet superconducting junctions. So there are quite a few properties, and one of the major direction in the discussion of these properties is that ultramagnets have no net magnetization. Hence, they should be very good for creating miniature devices. If you create, for example, memory here based on magnetic I would say magnetic materials, then at some moment you can miniaturize them to a small degree because there will be overlap between stray fields. So stray fields of these magnets will interfere. If they were made of materials that have no stray fields, it will be possible to reduce the spacing. So that brought us to actually study of finite size for interface effects in ultramagnets. Can ultramagnets be a savior? And if you create, for example, this memory bits out of ultramagnets, can we actually be miniaturized? To study this, working with my Norwegian colleagues, we use a simple model that has ultramagnetic ribbon, which is long along one direction, say y, and it has a finite size along x direction. We use two methods. We use continuum model, which is what I'm usually doing. We also use lattice model, which is done by our PhD student. So the idea was simple. Interface, it breaks rotation symmetry. And rotation symmetry is needed in alternates to protect vanishing net magnetization. Hence, if you have an interface, then perhaps you can expect some non-zero net magnetization. So maybe that naive and victorious picture of having device made of alternates is not so correct. So how to calculate? Well, we can start with Hamiltonian. We can add additional term to our standard Hamiltonian. We have kinetic part, chemical potential, and this is altermagnetic effective field. So here is going to the dependent part, which essentially tells us that spin up and spin down are split in the following way. And this part is essentially the same, but rotated by our. We can calculate wave functions in Agricola, right? Mechanic problem. We can calculate energies. It's pretty complicated relation, but its major part is that it actually depends on the altermagnetic splitting parameter. Here, S is the speed, spin up or spin down, and T1 is the strength of altermagnetic splitting. And this dependence means that our band structure will depend, and all properties that depend on energies and wave functions will also depend on the splitting. We can calculate density of phase, QC, and calculate magnetization. And what we obtain the following picture. It's pretty complicated, right? What we can see here is that nearby the boundaries, here and here, we see strong peaks of magnetization and we see oscillations of magnetization. So our prediction was actually correct. We have local magnetization created as the boundaries of this unconventional magnet. We can actually average it over the whole width of the ribbon. And well, we obtain pretty complicated structure, but if we make our ribbon wider and wider, we still have non-zero magnetization. So there is a magnetization generated in a ribbon. So there is no one-to-one correspondence with antiferromagnet, right? Where we would expect that there is no net application. Here, the sensitivity to the direction of splitting actually leads to magnetization generation. Well, I was able to check whether the same result holds in Max model. And there are different features of here. First of all, there is a strong dependence on how we terminate this ripple. This effect is known in antiferromagnets as odd even. So essentially, it's whether you terminate the boundary on spin down or spin up sides. It's tiny, but from there you can either create uncompensated unit cells as a boundary, or you can have completely compensated cells. And then we obtain the following data, where one can just notice that there is also magnetization at the interface. It's black line. So we have agreement with continuum model. Great. But then he did the same for antiferromagnet, and he also had the magnetization near the boundaries. And this magnetization actually came from this old even effect. So essentially, if you terminate your sample, that's you're creating the whole chain of uncompensated spins. So you just have whole chain of spin-ups at the interface. So, well, so what is the difference between antiferromagnets and these alternates? We realize that to prove this difference, we need to check whether the magnetization as a boundary is sensitive to disorder. Because in alternates, our low energy model predicts that it should be pretty robust. It essentially came from the Fermi surface. It came from Friedel oscillation. But what even here, it strongly relies how we terminate our ripple. So if we start to introduce disorder here, we destroy the perfect termination, and on average, I think we should have zero net magnetization. So I checked that. For that, he actually introduced a very interesting technique. He took the ribbon, took the inverted ribbon, and calculated magnetization, the sum and the difference. For antiferromagnet, since everything comes from the lattice, sum is just zero. And there is some difference that actually depends on strength of disorder. Here, the dark blue is a strong disorder, so it suppresses. For Altermark, on the other hand, the sum is non-zero because the sum comes from the Fermi surface and the difference comes from the light. And one can see that the sum remains pretty robust towards disorder. So the statement is that magnetization in Altermark indeed comes from Fermi surface states. Of course, it contains also this all even effect, but this is a separate effect. It's not the dominant one. And introduction of disorder was able to distinguish. Next idea was very straightforward. Interface is a different. It's a line different if we have a two-dimensional material. But okay, let's take a zero-dimensional different, just a point different. We know that there will be this big flow oscillations around different situation oscillations. This is the density of states, issue electron density. There will be the same oscillations in actual spin cycle. So essentially, there will be some density of states per spin. And we can see that has a characteristic debate symmetry. I'm using debate all the time. And if we integrate our energies, we obtain magnetization. And magnetization will show that there is a local magnetization centered on that difference here. So, as before, we show that presence of difference creates magnetization in our lines. We can go even further and finally combine altermagnetism with topology. So we were motivated by a recent study in chromium material. It was experimentally shown, experimentally combined with DFT results, that this chromium antimony realizes while electromagnetic phase. What is while? While semimetal is a material where you have bonds and conduction bands that touch a number of points, and such points have zero topological charge. In while electromagnet, these points also have non-zero spin projection. So we have spin up while points and spin down while points. Magenta and cyan. And since you have a topological material, you always have some boundary. Crystals are finite. This topological material, when it ends, topology elements disappear. There is no topology in vacuum, there is topology in material. So where topology goes, it should be somehow shunted at the boundary. And if we shunt the topology, we create specific boundary state called fermion. It was obtained experimental. Well, now you see that not all Arcus data is actually good enough. So this is an example of Arcus data. And I don't have Arcus glasses, so I need to be pointed where the particular state here. So they claim that there is a surface fermion state data by comparing it with initial data. I'm not going to go into details. But this result motivated us to take a much simpler model. We don't need to have a model where I think about 21 nodes in this material. We just took a simple model with my PhD student like this way and consider it as here, two arcs. We found that arcs, fermion arcs, exist and they are spin polarized. And furthermore, these arcs can have a different length. Different lengths, the spin polarization combined together means that we have more density of states of surface particles with a particular speed. So we have non-zero net quantization. And this quantization is going to be topologically protected because it relies on the existence of surface fermion states. Well, this is still a work in progress, and I hope we will prepare a paper this year, hopefully. But this is just another example of surface-related magnetization in unconventional lines. Okay, since my time is running out fast, then I will switch to last part of my talk related to unconventional odd particles. What are these materials? Before we're talking about ultramagnets that are even parity. Even parity means that, for example, if we at some point at this constant energy control, like momentum k to minus p, we are still at the band with the same spin projection. It's, for those who know, this is similar to D-wave superconductors, which even variety, or just an expansion in quantum mechanics. D-wave is even variety. Furthermore, in outer magnets, we break time reverse symmetry, but we preserve parity. So time reversal is actually the same as in many parallels. Now the question: can we have odd parity magnet? Natural question. We have even parity. Are there any odd parity where we flip k to minus k and we make a flip spin minus? The answer is yes. Such materials are known, but no one calls them actually odd parity magnets, and no one actually paid much attention to the energy spectrum. These materials are hell magnets. And here, one of them is, I think, europium phosphorus ring. And it shows this odd parity spectrum. So we have spin up here and spin down here. Now, the question is, but what is the local symmetry? Because these materials are usually pretty complicated as structure. And here is the advance of, again, Weber, Tomasz, and Hiro, and the student Anna. They show that, what a surprise, the lowest symmetry is P-wave. So the lowest odd parity is symmetry. And the advance is that they propose a material. This cerium, nickel, arsenic side that actually shows this P-wave structure. So one can indeed see that there are two counters with spin up, right? Spin down blue that are shifted with speculation. Here that was just the VT result and no model of that. And our advance was to develop such an effective model and describe simplest properties of this material that makes them different compared to antiferromagnets and outer magnets. What could be the simplest model of a P-wave magnet? It's just one-dimensional model. We cannot go to zero dimension, so we can go to a one-dimensional model. It's essentially a chain of spins, and the spins should rotate. Because one of the characteristic properties of this odd parity P-wave magnet is the presence of so-called tau-T symmetry, which is a combination of translation, yes, we can translate, and time reverse, we can flip speed. So we can translate and flip speed, and then this is the symmetry of this chain. And this is important. There is a theory argument that such type of symmetry protects P-wave structure from, let's say, periodic elements. And in the result, for such a model, we can obtain the best structure. And this shows the P-wave structure. We have red to the right, blue to the left. So with k to minus k, spin to minus k. In this material, of course, time reversal symmetry is preserved. Average. Inversion is broken. And the spectrum is odd parity, is odd. This is how this model looks like for condensates of type binding Hamiltonians. There's a coupling here, there's a constant potential, there is a coupling to spin, there's decoupling. But still, this model is pretty complicated. It has 8 bands. Well, it's not that nice to work with 8 bands. It's 8 by 8 Hamiltonian, it's big matrix. So we decided to develop an effective model where we cross-grain this chain. So we combine this, say, left and down to one sector, to right and up to another sector. And minimally, we need just to consider copying between the same sectors to get another model. Now this model is 4 by 4. It has a kinetic part, it has splitting part, and well, this part is coupling between different sectors. Furthermore, we don't want to work with in one dimension. One dimension, everything that is always P-wave. We want to distinguish between P-wave and higher order stack, F-wave. We need to go to 2D. In this case, we can replicate the chain. Well, technically, we actually also need, since we're working with metals and we don't want to have polarization, for this reason, we would like to switch to rotation, not in the plane, but in the plane perpendicular to our spin. And we can just add another chains and have materials in periodic in both x and y directions. Our Hamiltonian will obtain additional terms, but perhaps don't bother much with the dynamic model. But let's take a look at simplified low energy model where we perform expansion around the ground. The model is much simpler. It's the same kinetic term. It's quite well to have chemical potential. Now, instead of alternating even in K term, we have odd in K term here that determines our QSP. This term that is a remainder of this intersectoral point. And here's how the spectrum of this model looks like. It's a nice parabolic band, and it's polarized. It's spin up here, spin down here. And here is how it looks like when we fix energy. Sorry. So what can we do with this model? Our current model is essentially like a toy for theoreticians, so we can let's play this. We can calculate different properties, such as tunneling potential, Paul transfer, spin filtering, and these are just transfer properties. So far, no interactions. So what is the first one? What is a tunneling magnetic system? Imagine that you have two magnetic materials, and you combine them and form junction. If the spins in this material are in the same direction, it conducts with a certain conductance G up. Since spin up from according to the same direction, essentially is almost the same material, so conductance is high. But now let's flip one of the speeds, say here. And then it's a problem for material because we need to somehow move spin up electrons in the spin down material. So we need to flip spin, and this comes with some cost. And that's why this G up down is much smaller. And one can define TMR as following way. In our case, we can consider a combination of receiver magnets here and here. So it's a planar interface. And furthermore, we can not just flip spin, first flip spin, but also then rotate this direction of splitting on the right hand side. And here the result was obtained pretty trivial when the magnus is the same. We start with high TMR and it vanishes at pi over 2. Why it vanishes pi over 2? Because then this contour is essentially line on its side, and the flipping spin direction is not something. More interesting features appear when we consider different types of feedback magnets, different magnitude of spin splitting. For example, there's a peak valley here when this contour is larger, and this peak valley corresponds to perfect matching between contour spin. Other than that, they still vanish at pi over 2. And this is different from outer magnets, where the vanishing TMR occurs at pi over 4. So, well, we have different material with different analog methods. Let's move to the Watt transfer, which is another pretty simple properties of these magnets. We can just solve Boltzmann equation with simple relaxation band approximation. Here's the result, and the key feature of this result is that the conductivity along the open magnetic splitting, along this P-wave splitting, is smaller here than the conductivity perpendicular. The explanation is actually pretty trivial, and it's related to the fact that our constant energy contour, our current surface is anisotropic. Velocity is larger here, speed parallel, and smaller in this direction, which is quite. Another thing that I'm not going to show today is related to spin transfer through the second order spin response also. There's also a ground state current, spin current. But let's move to another issue, which is spin filtering. What is a spin filtering in our case? So we have some normal method here, we have T-wave magnet here. We apply electric current on as a T-wave magnet, and in this situation, it reflects both electric and spin current. So it creates some spin polarization. Well, it's not so drastic, but what makes it interesting is that this material has zero net magnetization, so we don't need ferromagnet. Now switching gears a little bit higher, we go from this non-interacting picture where we have really moving action to something interactive. And one of the pretty beautiful therapy is superconductivity. What are the specific properties of superconductivity in, let's say, ultramarines? And I can make a brief introduction to regular superconductors. So in superconductivity, we pair electrons with focus on a pair K minus K electrons. And this pairing usually is due to phonon interaction, phonon-mediated interaction. So when we do this pairing in alternates, in even polarity magnets, we pair with K minus K, and since it's even, we can pair only spin up and spin up. So natural pair of electrons. Both electrons will have spins in the same direction. This is going to be a spin triplet superconductivity. The still pair is a spin singlet, which is a regular channel that is PCS standard theory. The still pair in this channel, but for this we need to consider points as a spin up branch here, a spin down branch here, and this is actually just a point to the 2T, or it's a line in 3T. So the contribution of such pairings is pretty small compared to this dominant spin triplet superconductivity. There was recent research in this direction, several papers. Some of them predicted the realization of even more exotic superconducting states, but it's not go. What about direct magnets? What type of pairing can be considered there? Well, if you pair K minus K, the perfectly pairing spin down and spin up. So we have similar pair. So we have unconventional magnet. This sort of conventional type of superconductivity. Spin singlet. Of course, we can also realize the spin triplet here, but there is not going to be much different from alternatives. How can we check this? We can check this in a few setups. We can do tracy calculations, or we can do proximity type setups. Yes, yes. Here is the result of proximity one. Binding Hamiltonian. But basically, what do we have? We have S-wave spin singlet superconductor, and we are bringing P-wave magnet in this proximity, which induces P-wave splitting. We can consider a pairing between terminals, and what do we have? And actually, how do we form our P-wave magnet? We actually consider even more generic type of magnet that is just a helical magnet. It's composed of such chains with rotated spin of a certain period. The period is essentially distance between sides with spins pointing in the same direction. In the example we considered before, period was 4. So we have to spin up, spin to the left, spin down, spin to the right. Period 4. But here we're doing numerical calculations, lattice, and I have period. We start with period 2. Spin up, spin down. It's not different, right? Simple. And we can see that there is superconductivity, there is critical temperature, and it's very robust to the coupling to speeds, with a specific coupling strength. Critical temperature is high, and this means that superconductivity state remains robust towards the introduction of this old parity of the antiferromagnetic spin, which is expected. Antiferromagnets are stable, expected to protect investors. But then we can increase the period and we can go to 4 here. It's still pretty robust. The critical temperature is high, and we need to apply a high coupling to spins to break the repair, break superconductivity, which means that our P-wave magnets can coexist with the spin singlet superconductivity. If you go higher and higher in period, some values of period actually don't see that superconductivity is very robust. It becomes more and more as in ferromagnet. And a ferromagnet, as this ferromagnetism, it's just harmful to spin singlet pairing. It suppresses spin singlet pairing. How can one understand that? In antiferromagnet, we have a very rapid, or in P-wave magnet, we have a very rapid spin rotation. So on average, and under average I mean the size per pair, we see no net magnetizations. Everything averages to zero. But here, for larger view, we see a long chain, which looks like an almost homogeneous spin chain with almost homogeneous configuration on the length scale of the size of the Cooper pair. So here, essentially, Cooper pair lives somewhat in the magnetic field, and magnetic field is back of the magnetic field. It tries to break the spin singlet pair, it tries to orient spins in the same direction. Spin singlet superconductivity has spins pointing to opposite directions. So here is ferromagnet, here is antiferromagnet, and our low variety of magnets are here, pretty robust. We also did the same calculation for the intrinsic superconductivity, where we consider pairing inside material, no proximity effect, and we also found that it's almost the same as conventional S-wave pairing in almost all aspects, at least in a simple model. What is interesting then, so not everything is just the same. So there is some difference related to the fact that we have this odd parity or P-wave magnet. And we found that this difference can be manifested in transfer. Of course, again, transfer. So for this, we consider the following junction. We have P-wave magnet here to the left, superconductor here to the right. And there's always been a junction between any material and superconductor. Impinging electrons can be reflected as a whole. And whole per pair is a combination of two electrons and propagate in superconductors. Such a process is called anti-wave retroreflection. It's also the basis of all devices based on superconductor non-metal junctions. So what do we have in transport? We can consider longitudinal electric transport. We will see the following normalized conductance as a function of applied voltage phi. So model 2, phi2, because two electrons went to a superconductor. That's why it's higher than we would expect from conductance in the normal state. And then if you have a high barrier, like barrier between metal and superconductor, then we will see this coherence. So essentially, we just prove density of phase for superconductor. Now let's consider the property of P-wave magnet. If we have P-wave splitting that's perpendicular to the junctions along y direction, we have a transverse spin conductor. And it also inherits some of the properties of longitudinal electric conductors. So we have also a cancel here, we have coherent speed here. So superconductivity can enhance transverse spin transport in P-wave superconductor junctions or normal metal P-wave superconductor junctions. So there is pretty rich physics there too. Still needs to be explored in more depth. Before moving to the winners, I just mentioned a few materials that can realize this P-wave magnetism. One of them I already mentioned, has nice helical texture. And for magnets, I mentioned this European phosphate, and this actual material was recently claimed to be P-wave magnet. It's a nickel iodide too. But the reality, I think, is more complicated. So it's P-wave magnet only when you reduce a more complicated model of this material to some simple construct. But if you just consider an initial data for this material, it's more complicated. It has no tau symmetries that protect P-wave magnets. But it's surely what are they? So, since my time is run out, let me conclude and summarize the key points that I made in this talk. First of all, I introduce you to altermagnets and odd parity magnets as different types of unconventional magnets. I showed that interfaces that break the symmetries that protect vanishing magnetization can lead to surface magnetization and could be actually harmful for miniaturizing devices. I also derived the effective model of P-wave magnets, perhaps simplest minimal model for these materials, and applied it to spin and electric transport. I also showed that P-wave magnets, or actually any odd parity magnet, can perfectly coexist with simplest spin singlet S-wave superconductivity and can show also interesting effects, namely the transverse spin current. Finally, extensions that I'm currently working on is a combination of this altermagnetism and topology. Dynamical response in the okay, can we transform one type of magnet into the other? So interaction with light and structure light. And so finally, I would like to thank my collaborators on early you and Crispins and Axels participating in this global support. Thank you very much for your attention. Any questions?
Thank you very much, Pavlo, for the right talk. So let's start this question from the student.
When you introduced unconventional magnets, you showed that produce the extra atom, give us these dipole moments from the electrons. Is it the model kind of self-correcting in the sense that when that extra atom comes in and distorts the electrons in the lattice, that can also change the magnetism more, or is that such a small effect that you just leave it out?
If I understand what you correctly, you can start with antiferromagnet. Because essentially, you can go on the diagonal of it. Just move to this question. Yes. So let us start with this model, and you can have only this problem. Perfect symmetric. What would you like to have here? You like to have some symmetry between atom particles. In principle, if you can insert this atoms, means that you can consider not just direct hopping here, but hopping from here to here and from here to here. And this is what essentially this ellipse means. That electron tends to hop from here to here more than from here to here. Because just distance in atoms is large. First, you can construct an EFT model or a quadratic model, and then everything with the self-consistent. But you can just set everything like that. Other questions?
Yeah, I got two. The first one is just a clarification from right here. When you say weak or strong response, are you just talking about how they couple to your external driving field? Is that what you mean by strong spin response?
Okay, so then there's something interesting. So here, for ferromagnets, we know that it has a non-zero magnetization and can manipulate that magnetization, which is relatively large compared to that in 0. It couples to magnetic field. We can perform spin filtering. So all range of effects that is based on spin polarization of electrons is applicable here. For particular magnets, essentially bands are not spin split and they degenerate and can construct spin filtering out of antiferromagnet easily, for example. So many of the effects that rely on spin polarization just don't work with antiferromagnet. It's what I mean under weak spin response. Of course, there is some stuff that is related to logical part, interface defects, where it can show some spin response too. But this is like some leading. Here, for example, all electrons, in a very normal case, all electrons have particular spin polarization. Here, none of the electrons have spin polarization.
Okay, and my other one is just talk about the antiferromatic, where you said about on the edges where you terminate it's just yeah, there we go.
Okay, so here
That you end up getting magnetization on the edges, and I'm just curious. I mean, if you terminated at a different lattice spot, could you get a antiferromagnetic one that had both up responses or up?
well, see this one.
There we go.
Okay. I think it's possible. I actually don't remember the exact details of the numerics, and if you take a look at the paper, I think Eric did both cases. I think yes, it's possible. For example, here the was up here, and then was more or less up here. Yes, there doesn't really but here the thing was that in other magnets there are two effects. One is termination effect and the other ferromagnetic. The antiferromagnet is only termination effect. Here I think he wanted to do these terminations. Spin up, spin down. That's why it's spin up, spin down.
Okay, but you could have terminated at a different spot and got both of them. Okay, that's all I need.
Yes, 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 yes.
I was wondering about the relation about Haley magnets in general and what you call alternating magnets. Because Haley magnets, they can be commensurate or incommensurate, they can have very, very long pitches, right? Would they all belong to that class that you call alternating magnets, or do you need the commensurate magnets?
Yeah, I don't think that all of them are going to be alternating magnets. So some of them surely have alternating textures. I'm sure that not all of them are cubic magnets. Cubic magnet is a very particular class. Furthermore, I would like to have this tau T symmetry, and not all ferromagnets have it. So I would say that my class of ferromagnets is a subclass of modular class. This is my diagram. This.
So you were talking about open magnets, and you said you need to break time reversal symmetry. How do you break that time?
I don't need to break it, it's already from. It's essentially like antiferromagnetic, so there's a neon vector there.
Any kind of electron breaks them.
Well, I have a particular orientation, so if I do spin, it's different, but probably break diverse. So the same for antiferromagnets, all break diverse.
All kinds of them.
Well, as this is also the text, and for altered magnets, broken time reversal is the property.
It's what?
Is a property of the system. You cannot avoid it there. This
Have these unconventional magnets actually been built? Are these simulation results?
all the magnets were experimentally discovered. Go this one. This is hard. I'm not result of just crystal. This is material all synthesized, it's a real crystal, and here's the data just showed. This material, cobalt, neodymium ore, is also a real crystal that was synthesized. Actually, I think even here, there is a well, I'm not sure about whether it's exactly this material, so but the material from the same group. And here's experimental data. So this is a raw experimental data. This is a simulation. You're right. Any data that is very beautiful with simulation. Yes.
So when or at what condition antiferromagnet can become an altermagnet?
When you have a symmetry between copies. So essentially, there are two answers to this question.
How do you make?
I mean, how do you make
Different question, I'm sorry. It's a different question. From the point of view of spherical groups, you need to remove inversion or translation symmetry and replace it with subrogation. This can be achieved by somehow deforming orbitals, special here. From the
I should try to find out a non-symmetric space group.
Yeah, well, you don't need to access it, you need just a fabrication. That's true. Before. From a experimental point of view, you can try to perform interpolation. So we can say consider such a model and then displace atoms with empty position. This would introduce this symmetry between copies. There are other models how to create altermagnets. One of them is based actually on flotation, synchronizing them. Another model is based on twist. You can bring two van der Waals antiferromagnets, as far as I remember, and twist them by a certain angle. And it was shown that the system can realize altermagnetic state. So there are ways how to create them. So far, people were mostly hunting for properties. And there you don't need to do anything, you just need to find the right crystal where nature already realized there's this magic properties. But the difference I said again is inversion versus rotation.
The problem with the ultramagnet is, there's nothing to do with magnet. You can't measure anything. You only say from your RPS measurement. Right?
RPS, or you can do transport measurement, space measurement. You can try to look at magnets. Magnets are chiral, they're magnets, they're not chiral. The chiral means that the velocity in, let's say, x direction is different from velocity in minus x direction. So there are other effects that can be used in point outer magnets. But okay, RPS is a more direct one. The same happened with all of the materials. We saw beautiful RPS data and then we believe materials. Transport was not so amazing, I guess, for people.
So how did the land up getting European phosphide and nickel iodide as a keyword? Like, if it wasn't.
Okay, European phosphide is not a keyword. It's not keyword. It's a phosphide magnet. And I think people were absolutely clueless about this phosphide magnet or not. It's a whole study. They actually studied something completely different. They studied its response to magnetic field, because magnetic field tilts the direction of spin. But if you just take a look at the raw data that we get, it's legit, this operation. Nickel iodide. Yes. That was, I think, a targeted search. That, I don't, it's not, I think, I'm sure it's targeted search. This material. So this group, when it derived this proposed material, it looks beautiful. Yes, it's nice, simple square lattice, chemical spins. But well, if you talk to experimenters, I tried to talk to our local experimenters. Deepak said me that, well, it's heterostatic. No way I'm going to get it into my lab. Period. So people look at different classes of materials that also show some helical type of textures. Because the hope was that if you have this helical lattices, that's I discussed the simple model, it may realize the appropriate spin texture for electrons to generate the whole parity organization. And I think, actually don't agree that this material is still magnet. That's why I put it into the maybe all parity magnet. But it's all parity magnet, maybe not PWA magnet. That's why if you have the spiral textures, you most probably will have all parity. Alright. Just put this out easily. So mostly people, the workflow of people now is to use symmetry groups to classify materials. And by symmetry groups, identify which material may show all the quantities or not. Then try to perform DFT and determine whether the material is stable or not. The DFT is also actually pretty bad because there was a case of ruthenium oxide where people predicted by DFT that it is altered magnet. Even measured it to be altered magnet by some wrong technique, but then it was proven to be non-magnetic. So DFT is also a great result. So it's symmetry, DFT, and then experiment. Preferably RS or trust or combination. So
By transfer, what do you mean? Is it regular heat resistance or whole what kind of transfer?
Well, for D-wave alternative, I would like to see iteration. For D-wave alternative, I would like to see spin splitter effect, which is a generation of spin current perpendicular to the electric field. And it's actually different from Hall effect. It's not also separate either. This is what I would like to see. Also, there is a torque measurement, so we can generate a spin torque. In the virtual session works, but you can generate torque by many mechanisms. So I will not be sure. Since the data, RPS is one of the most reliable ones. Then you really need to show the data. We are going to show something.
Okay, is there any final quick question maybe? Okay, if this is not the case, let's thank our.